Good afternoon, ladies and gentlemen. In my talk, I will present to you some, I may say, recent developments in the fields of Weyl geometry and Weyl gravity, and its possible cosmological implications. I will be very brief in each of these points I may mention here. I will briefly present to you some information about Weyl geometry, about the conformal coupling between matter and geometry, the gravitational field equations, Newtonian limit, generalized Poisson equations, solar test systems, but I will insist perhaps a little bit more on the cosmological applications of these models. Probably you know that the first extension of Riemann geometry was done by Hermann Weyl in 1918, who proposed the first unified theory of electricity, of electromagnetism and gravitation. Anyway, Einstein strongly criticized Weyl geometry, and that's why it was abandoned as a unified field theory. However, in 1929, Weyl used the same ideas in the fields of basic electrodynamics and quantum mechanics, and he introduced the idea of the gauge transformations and of the gauge fields. These results from 1929 are fundamental in particle physics, and they were born from Weyl geometry as a result of works of Hermann Weyl. Now, what is Weyl geometry? Briefly, it can be defined as the class of equivalence between the metric and the vector gauge field. And these quantities are related by the first fundamental property of Weyl geometry, which is the idea of conformal invariance. So if we transform the metric and other geometric quantities in this way, we obtain a theory for a geometry that it is conformally invariant. This is the first fundamental property of Weyl geometry. The second one is that it is a non-metric geometry. That is, the covariant divergence of the metric tensor does not vanish, and this is fundamental difference as compared to the Riemann geometry. Anyway, one can define in Weyl geometry a lot of quantities similarly to Riemann geometry. What is important is that basically all quantities in Weyl geometry, denoted by a tile here, can finally be expressed in Riemann geometry, plus some contributions from the so-called Weyl vector field. I will not insist very much on the idea of the conformal invariance. A conformal transformation is in fact a stretching of all lengths. And this is due basically to a change in units. And this change in units is done by some factors, some functions that depends on the geometry or on the space-time location. And conformal invariance was introduced by Weyl, and its application as the gauge principle is fundamentally contemporary physics, be it elementary particle physics, condensed matter physics, etc. And here we arrive at a kind of paradox, another contradiction between elementary particle physics and gravitation. Because in fact, all the equations, all the fundamental equations in elementary particle physics are conformally invariant. And here you see a short list: the Maxwell's equations, the Master-Dirac equation, the electromagnetic Wickerson interaction, etc., are all conformally invariant, or by simple transformation they can be made conformally invariant. And here is the contradiction: while microscopic physics is conformally invariant, Einstein gravity is not. Is this a problem? It is not a problem, I don't know, but let's try to build gravitational theories, also adding to them the idea of the conformal invariance. And this can be done by constructing actions that are from beginning conformally invariant. And to impose conformal invariance, we need to start with Weyl geometry. And the simplest action, which is conformal invariant, is this one, defining Weyl geometry, and this tensor is the so-called Weyl tensor. There are some theories, the so-called conformal gravity, developed mostly by Mannheim, also called Weyl gravity, which is based fundamentally on this tensor. However, in my talk, I will assume that this eta tends to infinity, so we will neglect this contribution. So we are in a theoretical framework fundamentally different from the so-called conformal gravitational theories. Secondly, we interpret Einstein gravitational equations in their external form as a kind of symmetry breaking of this action. A symmetry breaking of the conformal invariance. Probably in the early universe, gravity was conformal invariant, but presently most probably it is not. So it may have occurred a spontaneous symmetry breaking. And how to implement the idea of the symmetry breaking in such an action. But before going to this, I will consider another problem, adding matter. How to add matter in a conformal invariant way to the Weyl action. There are several methods for this, several possibilities. Here I will concentrate on the coupling between the matter Lagrangian and geometry. In order to impose conformal invariance, we need to take the square of the Weyl scalar. And in this way, we obtain here a conformal invariant action in the presence of matter. And again, in the following, we will neglect this term, which was very much studied. And we have also free coupling constants in this theory. Now, to implement the idea of the symmetry breaking, a procedure, a very efficient and interesting procedure was suggested by Gilencia by linearizing the quadratic term in the action by introducing an auxiliary scalar field, by introducing a scalar field through this transformation. So, first of all, we obtain this action in which we have another degree of freedom, the Weyl vector plus the scalar field, and there is a non-trivial coupling between matter and gravitation. This action is already written in Riemann geometry. It is written in Riemann geometry. And it can be transformed again to this form. I will not go into these technical details. And the next step is to obtain the gravitational field equations, which take this relatively complicated form, which I will not insist on these equations. We have an equation for the Weyl vector. There is a lot of interesting mathematics you may enjoy. And similarly to other theories with geometry-matter coupling, the matter energy momentum tensor is not anymore concerned, and we can speak about the existence of an extra force. The Weyl vector satisfies some equations very similar to the Maxwell equations, but again I will not go into these details. But I will proceed to another issue, which is the Newtonian approximation. We can study the Newtonian approximation of this model, and we obtain finally this generalized Poisson equation. Generalized Poisson equation. And this equation can be solved under certain approximations by assuming that the square of the Weyl field is constant, that is in a finite region, and it leads to a modified Newtonian potential. And this modified Newtonian potential allows us to study the classical test of general relativity by using well-known methods I will not describe to you. In principle, this is a method based on the Runge-Lenz vector, and after doing some computations, we can obtain the diffraction angle of a planet in this form, and finally we can obtain the total motion of the perihelion of a planet. Here you all recognize the standard Einsteinian result, and this is the contribution which comes from the extra acceleration generated by the presence of the Weyl vector. Now this result can be compared with the observations, and we can obtain the numerical result that in fact the extra acceleration must satisfy this limit, that it should be smaller than 10 to the power minus 9 centimeters per second to the square. Those of you familiar with Mond certainly know that the Mond acceleration is 10 to the power minus 8. So I will not claim that this acceleration can explain dark matter, because we need an acceleration at least 10 times bigger. So the previous results also allows us to impose some conditions on the non-metricity, at least at the level of the planet Mercury, and the free coupling parameters must satisfy this constraint in order to pass the solar system tests. There are some other constraints on non-metricity, very interesting constraints by Delhomme, Young, Olmo, Romero. In this paper, they did determine the non-metricity on the surface of the Earth. And there is also this interesting result by Delhomme, Latour, Olmo, and Ronco, in which by using the Barba scattering, they specified the energy level of the non-metricity as being 1 TeV. All these results can somehow be put together, but I will not go now into these again technical details, but I will move to the cosmological applications of this theorem. I will adopt the standard Friedmann Lemaitre-Robertson-Walker in this very well-known form, and in the following, for simplicity, I assume that the Weyl vector has two components, omega 0 and omega 3. And with the help of these components, we can construct here the energy momentum tensor of the Weyl field. I would like to point out that this choice is an approximation, because once we introduce the third component of the Weyl vector, the geometry becomes anisotropic, and in principle we should use Bianchi 1 spacetimes, but again for simplicity and just for a general test of the equations, we will assume that in fact these products, omega 0, omega 3, etc., are very small. But before going to the Friedmann equations properly, I would like to introduce very briefly to the cosmological Weyl field equations, which are this kind of generalized Maxwell equations, but they do not refer to any electromagnetic quantity. All these quantities are purely geometrical quantities. Present theory has nothing to do with Weyl's unified gravity theory, electromagnetic potentials, etc. And if we assume that in fact the Weyl vector has all components and these components are randomly distributed, we can introduce averaging procedure based on this equation for the Weyl vector. And as a result of this averaging process, we arrive to the result that in fact the effects of the Weyl geometry can be modeled in terms of an effective fluid that satisfies a radiation type equation of state. So a randomly distributed Weyl vector acts as a radiation type fluid. Anyway, again, in the following, for simplicity of presentation, not to complicate things, I will ignore the effect of matter, the effect of proper matter, the baryonic matter, let's say. The matter component may be assumed to be present in the form of the scalar field and of the Weyl vector contributions. But anyway, these equations are approximate equations in which here we should add somehow the matter terms, but for simplicity, I am not doing this. And once we we have the Friedmann equations, we can transform the Friedmann equations in the redshift space, and we obtain that at least in some period of the expansion of the universe, the Weyl geometric model, the cosmological evolution equations of the Weyl geometrical model are given by these equations. At this moment, having these equations, we may have two possibilities. First of all, we fit these equations with observational data, a procedure which I don't like because I don't know how to fit. Or we can use another approach, namely, we try to predict from these equations the observational data. That is, instead of following the observational data, we let observational data follow us. And this can be done by guessing some values for the model parameters, which are those three coupling constants. Anyway, after by introducing this kind of predictive type approach, it turns out that for these values of the parameters, we obtain some kind of consistency with the observational data, which are from some Hubble data. And also the model describes very well the lambda CDM results, at least at the low redshift. And I would like to mention that in these plots, the value of the Hubble, present day value of the Hubble constant is 67. 67. Okay, this is a deceleration parameter which shows some, for some values of the parameters, shows some differences with respect to lambda CDM. And finally, from this model, we can obtain some constraints on the Weyl parameter couplings and the present day value of the Hubble constant. The Hubble constant in this model, H0, the present day value, becomes a function of the coupling parameters and of the Weyl vector. I don't claim that this model solves the Hubble tension, even that you can fit the data probably with any value you wish of the H0. Even if we solve the problem of H0, we just transfer the problem to some other coupling constants whose values must be determined and interpreted physically and so on. So even that there is no, in some sense, there is no Hubble tension in this model. This is not a solution because still we need to find out if the coupling constants can disrupt the early universe, if the coupling constants do not vary with the redshift, etc., but who knows, after doing all these investigations, maybe some results of these Hubble tensions may appear, and I will conclude my talk. So Weyl geometry, first of all, we present a bridge between elementary particle physics, which are based on the gauge principle, and Einstein gravity, which in the present formulation is also based on the gauge principle. And I did not discuss the very important relation between standard model and the elementary particles Weyl geometry and its relevance for the standard model. But anyway, the standard model can also be embedded in a Weyl geometric framework, and in elementary particle physics, this is done without any additional degrees of freedom. And perhaps from the presented results, we may reach this conclusion that Weyl geometry may provide a natural explanation of the present-day cosmological dynamics. Who knows? Maybe it is so, maybe it is not, I don't know. And finally, Weyl geometry and this model has also some observational consequences that can be detected even at the level of the solar system. If that small extra acceleration induced by the presence of non-metricity could be sometimes, probably in the future, measured. If it exists, it will put at least some constraints on the free parameters of this theory. Thank you very much for your kind attention. Yes. Yes, please.
Okay, I would just say, when you selected the Monde behavior,
yes.
Can you select also a related characteristic length in kilopascal, for example, that could be compared, for example, with galaxies?
Yes, in principle this can be done, but I didn't do.
Okay.
So yes, but it's a very good idea. Yes, thank you. There are also characteristic lengths. It is easy to construct.
Because I'm saying this because if you do this with Monde,
yes.
in Monde you can get a very characteristic length which is 3 kiloparsec,
yes.
which is connected with acceleration by neutron. I think that you can do the same here.
Yes. Yes, this can be done. Thank you for the suggestion.
Go ahead.
Yeah, thank you for a really nice talk. Yeah, so I'm trying to understand the physical significance of this equation. So non-metricity and non-conservation of energy momentum. So that's, I mean, that would usually in thermodynamics be related to sort of a coarse-grained system of degrees of freedom, where you have maybe a or something, so yeah, something that emerges from neglecting degrees of freedom at smaller scales. Is that?
So I'm not sure that I understand the very well question.
I'm just trying to understand like the non-conservation of energy momentum.
Yes. Yes.
You can have that in classical.
Yes. So the non-conservation of the energy momentum tensor is not particularly mysterious in this model because it is a specific of all theories in which there is a coupling between matter and curvature. There is a very large number of such theories. One of them is the so-called F of R theory. We do have an FRT theory, FQT theory, and so many theories. Once we couple geometry with matter in a way or another, the energy momentum tensor is all the matter is not concerned. It's a very general result and appears here somehow in a standard way. How to understand physically this problem is another complicated issue. It can be interpreted in terms of a fifth force that appears because the motion is not anymore geodesical. It can be interpreted in terms of some particle creation, and it may have some other interpretations, but these two are those I know. So extra force and particle creation.
Yeah, actually, this theory arises naturally, the interaction between dark energy and dark matter arises from the geometry. Okay, very good talk. My question is, in the end, you said that H naught is a function of these extra parameters.
Yes.
So the $1 million question is the following. The value of these parameters in order to elevate the tension are consistent with the thermal history of the universe, or you need two large alpha, yes, there, and psi in order. So is it consistent to solve the tension or elevate it and not destroying the thermal history of the universe due to the value corrections?
Yes, as I mentioned, I do not know what is the situation in the universe because I didn't study this. So I cannot give you a concrete answer. Maybe it will solve, maybe not, but it requires further work, which I hope I can do. about these constraints, there is something funny in the sense that elementary particle physicists expect to determine these parameters from cosmology, and I guess cosmologists do expect to determine H naught from these parameters. So who will be the first to reach a better precision? I don't know, but there are two directions from which results may come. Elementary particle physics and cosmology, when cosmologists will agree what is the present day value of the Harko constant, which I would like to point out must be only one. There may be no any tension between them because there is only one present day value of the cosmological constant.
Okay, let's leave the rest of the conversation for the break. Thank you.